So here's another surface integral. This one is a little different than the one before because the other one had a basic parametrization. This one is a little more fancy, which means it might involve a little bit more work, especially because it's a sphere. So if you see a sphere, that means it's going to be a lot of work, and you'll see why. So here we want to find the surface integral, and S is this hemisphere with x squared plus y squared plus z squared equals 4. So if I were to kind of draw what we're looking at, we have this hemisphere. We don't want all of it. We only want it when z is positive. So we got this little cap. Okay, so imagine that it kind of looks like that. Okay, so we got this little cap. And we want to find pretty much the surface integral of this guy. So imagine again the mass, and in this case, the density of this particular hemisphere is defined by this guy. So I guess we're just finding the mass of this little object. Okay, now notice that my hemisphere has this type of equation. So to parametrize it, usually, as if we saw the last problem, we would want y equals something, z equals something, or x equals something. Okay, so we want it to be as a function, like z is equal to as a function of x and y. And notice that you can't quite do it with this one, because if you move everything over, you're gonna have to have a square root, and that's just gross. So we need to figure out what is another way that we can parametrize a sphere. And the way that we do it is using spherical coordinates. Okay, so how would we use spherical coordinates? So remember that in spherical coordinates, we have x equals rho cosine theta sine phi, y equals rho sine theta sine phi, and then z equals rho cosine phi. So this will be kind of my pairs of parametric equations, or not my pairs, my triples. Now, notice that when we look at parametric equations, we only want two variables, and we have too many of them. But we know what rho is. Rho in this case is going to be this 2, because the square root of 4 is going to give me a 2. Okay, so my parametric equation is going to be x equals 2 cosine theta sine theta. My y is going to be 2 sine theta sine phi. And my z is going to be 2 cosine phi. Again, you can write it as r of theta and phi. So those are my two variables that I'm using for my parametric equations. And I can write them as a vector function. So 2 cosine theta, oops, no comma. 2 cosine theta sine phi. Oh, this should be sine phi. Then this should be 2 sine theta sine phi, then 2 cosine phi. Okay, so now what we're going to do, we need to figure out what are we going to do when you have a special type of parametrization like this one. So if you have a different parametrization than the other one, in order to find the surface integral, the double integral over the surface of f of x comma y comma z ds is going to be equal to the double integral over d. And what we're going to do is we're going to plug in whatever parametrization I found into the function and then multiply it by the magnitude of RU crossed with RV. And then this is going to be dA. So I will tell you right now that this one, especially in spherical, is not going to be that great because you have so many different things here. Okay? So I need to figure out what that guy is. Now let me write it in the form that I have it now, because I don't have u and v. I have theta and phi. So the magnitude of the partial derivative of theta crossed with the partial derivative of phi. So many letters. dA. Okay, so I'm going to try to find that. So first, let me look for the cross product. This is not going to be fun. I'm going to tell you that. Okay, so let's start off with the cross product. So r theta cross r phi. So we're going to start off with I. Let me make some space. J and then K. Okay, I didn't need that much space, but whatever, doesn't matter. Okay. All right, so now what's going to go in the first row? So in the first row, or after the ijk, is going to be the partial derivative with respect to theta. So what I'm going to do is I'm going to take every single one of them. Let me write them in yellow. So I'm going to take every single theta, or every single component, and take the partial derivative with respect to theta. So starting with the first one, taking the partial derivative with respect to theta is going to give me negative sine. So that's going to give me negative 2 sine theta sine phi. Then I'm going to look at the next component. Take the derivative with respect to theta. That's only this guy. So the derivative of sine theta is cosine theta. So I'm going to have 2 cosine theta sine phi. Let me write the j this way. Okay, and now we're going to take the partial derivative of the third component with respect to theta. Well, there's no thetas there, so this is a constant, so it's going to be 0. So that's that. And then what we're going to do, we're going to look at our phi. So now we're going to take the partial derivative of each of them, but now with phi. So the partial derivative with respect to the first one, with respect to phi, sine phi is going to be cosine phi. So we're going to have 2 cosine theta cosine phi. Then you're going to look at the next one, partial derivative with respect to phi. It's going to give you cosine, so it's going to be 2 sine theta cosine phi. And then the last one will be just negative 2 sine phi. All right. Okay, and now what we want to do is we want to take the cross product. So this is going to be a lot of crazy stuff. Okay, so let me put it in a different color. So this is going to be equal to the I component, and I'm going to take the cross product. So that's going to be 2 cosine theta sine phi, 0, 2 sine theta cosine phi, then negative 2 sine phi. That's the I components. Then j, we're going to cross that out, so it's going to be negative 2 sine theta sine phi, 0, 2 cosine theta cosine phi, and the next one, negative 2 sine phi. Then plus k hat, negative 2 sine theta sine phi, then 2 cosine theta cosine phi, 2 cosine theta sine phi, and then 2 sine theta cosine phi. Okay, so a lot of crazy things in here. And hopefully I didn't make a mistake, because if I made a mistake, it's going to be terrible. Okay, so it all looks kind of right. So now let's go ahead and combine everything together. So combining everything, I'm going to get I hat. So I'm crossing this guy out. What I'm going to end up getting is negative 4 cosine theta sine squared phi, and then the next one's going to go to 0, minus j hat. Here we're going to cross this guy out, so it's going to be positive cosine, no, 4, positive 4 sine theta sine squared phi, and then the other guy's going to go away. Then plus k hat, this one's going to be the crazy one. You're going to have negative 4, so crossing it again. So negative 4 sine squared theta sine theta, sine phi, cosine phi, then minus 4 cosine squared theta sine phi, cosine phi. All right, so a lot of stuff. Okay, so let me clean this up a little bit. So you're going to have negative 4 cosine theta sine squared phi in the I hat direction, minus 4 sine theta sine squared phi in the j hat direction. And then here what we can do, okay, so let me pull out this negative 4. You can see that you got negative 4s there. So I'm going to pull that guy out. And then something else that I'm going to pull out, you can see that I got this sine phi cosine phi going on. So sine phi cosine phi. And what's left over, this is actually really good. What's left over is just squares. So those guys are just going to go to 1. So all I'm left with now is just k hat. All right, we're done with the cross product. But now what we got to do is something even more horrible. Now we got to take the magnitude of this guy. So we're going to take the magnitude of r theta cross r phi. So we're going to have to take the square root of all this guy and square them. Okay, so now when we square the force, I'm going to skip a couple steps. If I square the force, I'm going to get 16, and I can factor that because I'm going to have a 16 every single term. And then in the other guys, it's just going to be them squared. So cosine squared theta. This guy's going to be to the 4th power because there's a squared. So sine to the 4th phi. Then plus sine squared theta, sine to the 4th phi. And then the other guy, sine squared phi, cosine squared phi. All right. So the square root of 16 just gives me 4. Okay, so I'm just going to have 4 there. And then here, what am I going to do? So I'm going to take a look at the first two guys. So these two guys, I'm going to look at them first. And I notice that I have a sine to the 4th there. Okay, so I'm going to take out a sine to the 4th. So sine to the 4th power. And then phi. And notice that in the inside, I'm going to be left with the cosine squared and the sine squared theta. So all I'm going to be left with is that's just a 1. So that's just that times 1. And then the next one, this guy, well, that one just stays there. So it's just going to be sine squared phi, cosine squared phi. And you can see now that I can factor out another guy. I can now factor out a sine squared from both of these guys. So I'm going to have sine squared phi. And the inside, I'm left with sine squared phi plus cosine squared phi. Notice that's just going to give me 1. The square root of sine is going to give me absolute value of sine, but since we're only looking at the positive hemisphere, this is just going to go to 0. Or phi can only be positive, so you're just going to get 4 sine phi. Oh, okay, so that was rough. But now we kind of almost are done. We're almost done. So all we got to do now is plug everything back. So let's go back. So we did the cross product and we found the magnitude. So now that's what we're going to plug in here. And here we're going to plug in the 4 sine phi that we just found out. Now what we got to do is we got to take our integral and we're going to plug in xz back in there. Okay, so let's do that. Okay, here we go. So now that we finished that, we're going to have the double integral over the surface of x squared z plus y squared z ds. So let's plug everything in there. So this double integral over the region D. So x in this case is going to be that 2 cosine theta, 2 cosine theta sine phi squared. Z in this case is going to be equal to 2 cosine phi plus y squared in this case is 2 sine theta sine phi. This whole thing is squared. And then z is going to be 2 cosine theta. So that's 2 cosine phi. So that's just me plugging it into my function. Now ds in this case is going to be what I just calculated, which is basically so let me go back up. So remember that this ds just corresponds with the cross product. So the cross product times dA is going to be this 4 sine phi that I just found out what that was, dA. Okay, so let's go ahead and simplify a couple of things. So we're going to have the double integral over the region D. So this guy's going to give me 4, because you got a 2 times 2 gives me a 4. Then you're going to get, and then another 4 on the outside. So let me just distribute this so that I can just kill 2 birds with 1 stone. So I'm going to get 2, I should probably do it this way, because it's a little confusing. Oh no, the whole thing is squared. Okay, let's see. So I got 2 squared, that's going to give me 4, times this other 2 is going to give me 16 And then times 4. No, wait a minute, that's wrong. 4 times 2 gives me 8. Times 4 gives me 32. Okay, then you're going to get a cosine squared. Okay, and then you're going to get a sine phi. Sine squared phi. So that's what I'm going to get in there. Okay, and then, whoa, you also have that other sine phi. Oh, this was a terrible idea, doing all of them at the same time. Okay, sine cubed phi. Okay, and then we have that cosine phi on the outside, cosine phi. Okay, so that's this guy squared and then distributed. Okay, and then plus, now you have 2 squared is 4, times 2 gives me 8, 8 times 4 gives me another 32. Then I gotta get a sine squared in here, theta. Then you got a sine squared phi, and then you got that extra sine squared phi on the outside. So you're gonna get a sine cubed phi, and then you're gonna have a cosine phi. And it's gonna be not dA, because it's gonna be the 2 different variables that I have, so it's gonna be d phi, d theta. Okay. Now, what would be my limits of integration in this case? Oh, let's figure that out in a second. Let's factor out a couple things. So I can take out a 32. I can take out a sine cubed phi. I can take out, what else? A cosine phi. And notice that all that I'm left with is just this cosine squared theta and this sine squared theta. And then d phi d theta. Okay, so that goes away. That's just the 1. Okay, so it's over the region D. So all we're just left with is just this 32 sine cubed phi cosine phi. Okay, so at least it went a little bit better. Okay, and now we're going to figure out what phi is. So phi in this case, if we're looking at the hemisphere, we only want half of it. So it's going to go from the positive z-axis all the way until I get to the y, which in this case, that gives me a 90-degree angle, which is pi over 2. So this is going to be from 0 to pi over 2. And then my theta value is obviously going to be from 0 to 2 pi. Okay, so notice that there's no theta, so you're going to have the integral from 0 to 2 pi of d theta, and then the integral from 0 to pi over 2 of 32 sine cubed phi cosine phi d phi. So this first guy is going to give me 2 pi. Then you're going to get this 32. This guy is going to give me a sine to the 4th phi by using substitution. U substitution. This is just a U sub. From 0 to pi over 2. This is going to give me 16 pi. No, that's wrong. Well, this is just, what is this? 4. And then that's going to give me a 2. That's going to give me 16 times, 16. And then times the sine 4th of pi over 2, because that's the only one that's really going to give me anything when I'm missing a pi. It's going to give me 16 pi. And we're finally done with this terrible problem. Okay. So yes, with spherical coordinates, it is a mess. Now, we're probably going to do one more problem, but it's not going to be, well, it might be like this. But spherical, whenever we do the cross product, is just a big fat mess. It's just a lot of work. But at least our integral got a little bit better. Okay, but that's how you do that problem.